We're rounding out this unit talking about inequalities, the same way that we rounded out the last couple of units. Specifically, today we're talking about polynomial and rational inequalities. So since this unit we've been talking about polynomial equations and rational equations, all we have to do today is add in things that instead of having an equal sign have a greater than, less than, greater than or equal to, less than or equal to. You do have to remember some of the rules that we have where a greater than or less than, typically we're going to have an open circle. Greater than or equal to, less than or equal to, we're going to have a closed circle. And then we'll have to figure out the regions that we're shading. And then we'll also have to write our answers in interval notation, which in interval notation, greater than or less than involve parentheses, greater than or less than or equal to involve square brackets. If we consider what a polynomial equation is, and we're talking about an inequality, if we have this polynomial equation, for example, f of x equals x squared minus 6x plus 5, and we have an inequality that says that this is either greater than 0 or less than 0, what we're really talking about, and this should help you visualize a little bit, what you're really talking about, if it's less than 0, is where this polynomial dips below the axis, right? This is where f of x is less than 0. Or where the polynomial is above the axis. And where it's above the axis is where f of x is greater than 0. You could describe both of these regions with interval notation. So it's less than 0 between -1 and 5. It's greater than 0 from -infinity to 1. I'm sorry, that's a positive 1 to 5, not a -1. From -infinity to 1, and then from 5 to infinity. Right? We're talking about where does this happen? Where is it on the x-axis? Through what domain is it greater than 0? Or through what domain is it less than 0? Here are some steps that we can use to solve inequalities. They're not linear. So polynomial inequalities, rational inequalities. What we want to do is arrange everything so that it's equal to 0 or greater than 0, less than 0. We want it to where 0 is on one side. Then we want to solve it as if it were an equation. We're going to put those solutions that we got to the equation on a number line, and then we're going to check around that to see which pieces of the number line, which ranges work, which actual parts of the domain work. Let's look at an example. So in this inequality, 3x, x minus 1, greater than 10 minus 2x. Step 1 is to set it equal to 0. We want it equal to 0. So if I distribute on this side, I'd have 3x squared minus 3x greater than 10 minus 2x. I need to get everything on one side and 0 on the other side. So what I can do is add 2x. 3x squared minus x greater than 10. I can subtract the 10. 3x squared minus x minus 10 greater than 0, and then I can try and solve this as if it were an equation. And the way that I would solve it if it was an equation is I would use star method. 3 times -10 is -30, -1 on bottom, 3 and 3. Let's see, -6 and +5 seem to work here to multiply to -30 and add to -1. This is the same as 1 over -2. So then my two factors here are x minus 2, 3x plus 5. And so the solutions here would be 2 and -5/3. I'm going to put those numbers on a number line. -5 over 3, 2. And I'm going to just find some numbers in between those, to the right, to the left. I'm going to try and find numbers in every single piece of this number line. Now, going back to talk about our parentheses, brackets, open circles, things like that, since this is strictly greater than, in our original problem it's strictly greater than, we know we need to have an open circle, not a closed circle, right? Because it's greater than, we're going to have an open circle. And now to figure out whether it works in any of these, we're just going to sub into the original equation. So I'm going to sub into the original equation up here any of the values that are not already have an open or closed circle. So for example, I could sub in -6. So I'm going to type in my calculator, 3 times -6 times -6 minus 1. And I get, for -6, I get 126 is greater than 10 minus 2 times -6, 22. Is that a true statement? Yes, it is a true statement. And so -6 gives me a true statement. I can shade towards -6. Let's try 0. If it gives me a true statement, I'll shade it. If it doesn't give me a true statement, I won't shade it. 3 times 0, parentheses 0 minus 1, I get 0. Greater than 10 minus 2 times 0, I get 10. Is 0 greater than 10? No, it's not. I'm not going to shade at 0. I'm putting a little red X to notify myself that I've already checked something in that region. Let's try 3. 3 times 3 minus 1 gives me 18 is greater than 10 minus 2 times 3 gives me 4. Is 18 greater than 4? Yes, it is. And so we can shade that way. All right, to describe the shaded regions, I could use interval notation. It's shaded from negative infinity to negative 5/3. Then it's shaded again from 2 to infinity. If these had closed circles, then I would use a square bracket. Since ours just have open circles, I'm just using an open parentheses and a closed parentheses. That is my interval notation solution to that inequality. Here's another one. Why don't you take a second and try this one? Here's what my solution looked like. Got it equal to 0. Did star method. Found 7/2 and -3 to be my two solutions. Put those on a number line. Positive 7/2 is just above 3. It's 3.5. -3 is to the left, and I saved the best part for last so that you guys could see this happen. I need to pick a number in each range. So like -4 is to the left. 0 is in the middle. 5 is to the right, and I'm just going to check and see if they give me a true statement. So if I say 2 times -4, parentheses, -4 minus 1, I get, in my calculator, 40 is less than, on the right side, 21 minus -4 is 25. Is 40 less than 25? No, it is not. So -4, I will not be able to shade there. If I sub in a 0, 2 times 0, parentheses, 0 minus 1, I get 0 is less than. 21 minus 0, I get 21. Is that a true statement? Yes, it is. All right, sub in a 5. 2 times 5, parentheses, 5 minus 1, I get 40, less than. 21 minus 5, I get 16. Is 40 less than 16? No, it is not. So I will not shade in that region. Do shade in that region. So then in interval notation, my solution is everything from -3 to 3. Oh, no, that's not 3. I'm sorry. -3 up to 7/2. Sorry. That number right there is positive 7/2. Here's another very similar problem. This one's a polynomial inequality. First thing I need to do is get everything over to one side. X to the 4th plus x to the 3rd minus 8x squared minus 12x greater than or equal to 0. I can solve this by the same methods that I have been. So I can say first I could take an x out of here. X to the 3rd plus x squared minus 8x minus 12 greater than or equal to 0. Notice the greater than or equal to. I know I'm going to have closed circles on my dots this time. All right, we could try grouping here. It's not going to work. We're actually going to have to try synthetic division to find at least one of these solutions. So if I say in synthetic division, I'm just going to test out some of these numbers real quick and see if they work. A to the 3rd. So here's what I'm doing. I'm setting up my synthetic division. 1, 1, -8, -12. And I'm trying numbers like -1. Remember, you're going to try numbers specifically that are factors of this, right? So positive and -1, positive and -2, positive and -3. Let's see here. Here we go. Negative 1 didn't work, but negative 2 seems to work. So if I bring down the 1, negative 2, negative 1, positive 2, that would give me negative 6, would give me positive 12, would give me 0. So I know that that did work. Since this has 3 terms, I can do star method with it and hope that it works. And negative 6, oh no, that doesn't work. How about negative 3 and positive 2? So that'd be x minus 3, x plus 2. So that'd be positive 3 and negative 2. So I got positive 3, I got negative 2, I got another negative 2. I got here, x equals 0 would be a solution. Since we knew we needed 4 solutions because our degree was 4, we do have all 4 solutions listed here. That says equals, but x is not equal to those, right? Those are just our critical points on our graph. And so if I start at 0, negative 2, 1, 2, 3, I can put as many points on this number line as I want to. Since this is greater than or equal to, I know I'm going to put closed circles around my points. So at 3, at negative 2, and at 0, I'll have closed circles. Now we need to check points in all of these ranges, right? So in between each point and outside of each point. So if I try negative 3, for example, negative 1, positive 1, and positive 4, that will give me a good idea of what's going on in this range, this range, this range, and this range. I want to check something over here, something here, something here, and something here. All right, let's say I sub a negative 3 into my original equation. Again, I'm going all the way back to here. I'm going back to the original when I sub it in. That just ensures that I am not making a mistake. Negative 3 to the 4th minus 12 times negative 3 is 117 is greater than 8 times negative 3 squared minus negative 3 to the 3rd. That's a 99. Is 117 greater than 99? Yes, it is. All right, sub a negative 1 in. Negative 1 to the 4th plus 12 times negative 1 gives me a 13 is greater than or equal to 8 times negative 1 squared minus negative 1 cubed. That's a 9. 13 greater than or equal to 9. Yes, that's also true. How about a positive 1? 1 to the 4th minus 12 times 1, negative 11. 8 times 1 minus 1, 7. Is negative 11 greater than 7? No, it's not. And then positive 4. 4 to the 4th minus 12 times 4 is 208. Is 208 greater than or equal to 8 times 4 squared minus 4 to the 3rd, 64. Yes, it is. So we can shade that way. And so our interval notation is everything from negative infinity up to 0. And then everything from 3 to infinity. Notice that it does not stop here at 2. It does not stop. It just carries on. It's shaded all the way to the 2, then all the way to the left of the 2. It's shaded it from all the way out here, all the way to here. It does not, the shading doesn't stop. That's why my interval goes from negative infinity to 0. If we thought about this polynomial, if we take a second, back up a second, think about this polynomial right here. If we were to graph that, here, let me do a black star to show you. If we were to graph that, we know that our solutions are at 1, 2, 3. Our x-intercepts at 3, negative 2, and 0. Using the end behavior, it goes up on the right and up on the left. And since negative 2 is listed twice, the multiplicity is 2. It's going to bounce off there. And so my graph is going to look like this. And so if I'm talking about where this graph is greater than or equal to, here, greater than or equal to 0, then that means it's greater than or equal to 0, all of this space, right? For all of that space, it's greater than or equal to 0. Here it's less than or equal to 0, so not here, but then it's greater than or equal to 0 again from here over. If you compare that to our interval notation, it's greater than or equal to 0 from negative infinity up to 0, and then again from 3 to infinity, which is exactly what we have written down. All right, here I have some very similar inequalities. You could take a second, pause, try and figure these out on your own. Here's what happens when I try and solve these. If again I was to look at this as a graph, 4x squared minus 12x plus 9, I only have one x-intercept. That's it, positive 3 over 2. 1, 2. So positive 3 over 2 is somewhere right there. This graph is facing upwards on both sides, and so I know my graph has to look like this, right? And so if I'm asking each of these questions, where is it less than 0? Never. It's never less than 0. Where is it less than or equal to 0? Only at 3 over 2. Right? At that point right there, it's equal to 0. Where is it strictly greater than 0? It's strictly greater than 0 from here to here, and then from here to here. Here it's equal to 0, right? It's not greater than 0. So it's strictly greater than 0 from negative infinity to 3 halves, and then from 3 halves to infinity. And where is it greater than or equal to 0? Well, it's greater than or equal to 0 here. It's equal to 0 here, greater than or equal to 0 here. So that's from negative infinity to infinity. A rational inequality, it's going to work the same exact way. It's going to work the same exact way. The one extra thing that we have to keep in mind is the restricted value. So what's going to make the bottom 0? So here, x equals 2 is a restricted value. I'm going to list that over here to the side, right? And any number that makes the bottom 0 ever, any number that ever makes the bottom 0 is going to be an open circle on our number line. So x equals 2, we know it's going to have an open circle right off the bat. All right, to solve this rational inequality, what we can do is we can multiply both sides by the denominator. So I'm going to multiply by x minus 2, so that on this side, the x minus 2's will go away, and I'm left with 4x minus 5 less than or equal to 3x minus 6, because I'm multiplying the 3 by both. I can subtract 3x from both sides and get x minus 5 less than or equal to negative 6. I can add 5 on both sides and have x less than or equal to negative 1. And so negative 1 is my next critical point. It's less than or equal to, so I can put a closed circle. And again, I can just check points. Here, since my statement at the bottom explicitly says x is less than or equal to negative 1, I know I'm going to be shading to the left. And so my interval notation for this solution is everything from negative infinity to negative 1. And it just so happens we don't even have to worry about the 2 because that's outside of that range, right? It's not inside that range. It's not going to affect us. All right, here's another. Restricted values. X cannot equal 2. X cannot equal negative 3. Those items would make the bottom of that fraction 0. When you multiply both sides by each denominator, you get 3 is greater than 2. You don't get something that even has an x in it anymore. Look at this. This is what happens when you multiply. Subtract x from both sides. You get 3 is greater than 2. That is always true. And so our answer is all real numbers, or our answer is negative infinity to infinity. So our graph is going to be everything from negative infinity to infinity, except these numbers right here. So everything except for negative 3 and positive 2. And this is what your interval notation looks like in the end. All right, we have another one. This one's cubic. This looks very similar to a problem that we did earlier. Again, you could take a second and pause this video if you need to. This one looks like we can actually solve it by grouping instead of having to do synthetic division. So what I can do is say, take an x squared out here, and take a 4 out here. If at any time you need to go back and review those factoring methods, those are always still at the beginning of this course, right? So at the beginning of the course, the very first lesson was on factoring. That was a review lesson. You sort of come into this class with me hoping that you already know how to factor, right? And so the very first lesson is just a review. Factoring is something you should know when you come in. Once you get it factored, you can look for things that make these factors 0. We can put those items on a number line. Negative 5 over 2. Negative 5 over 2. That's negative 2.5. Each of these items is going to have an open circle because of that less than. They're going to have an open circle. So open circle here, and an open circle at 2. I'm trying to find some items in each region, and I'm again split into 4 regions. If that's negative 2.25, or negative 2.5, I'm sorry, we could call this negative 2.2, right? Some item in between. We just need an item in between negative 2 and negative 2.5. And so the regions that I'm going to check, you know what? We could do the regions again. Here's two ways of solving this. I'm going to actually do this a different way, but you could check negative 3 in your original equation, negative 2.2, 0, and 3. And you're going to check and see if they give you a correct solution or not. If they don't, you're going to put an X. If they do, you're going to shade. Here's the way I'm going to look at it, though, is I'm going to think about it as a polynomial that I'm going to graph, right? And so my solutions are at 2, negative 2, negative 2.5. And my polynomial is going to be facing upwards to the right and downwards to the left based on this first exponent and coefficient. And so it's going to actually go like this, swoop back up. And what I want to know is, where is this thing less than 0? Where is it less than 0? Not equal to, but where is it less than 0? It's less than 0 in this region right here. So I know it's less than 0 all the way up to negative 2.5. That's out here. And it's also less than 0 in this region right here. It's below the axis, right? In that region right there, between negative 2 and positive 3. This is negative 5 over 2. This is negative 2. That's positive 2. And so it's less than 0 in this region. And that kept me from having to check so many numbers, right? Because I know how to graph these, which you should know as well based on the previous sections in this unit. It saved us a little bit of time having to check a whole bunch of numbers. And so our interval notation's from negative infinity to negative 5 over 2, and then from 2 to 2. Those are our intervals where it's negative. Basically, the 2 highlighted intervals there are where it's negative. I would take a second again and try and solve this one on your own. First, I'm noticing that t cannot equal 7 over 2. So that's the first thing I'm going to put on my graph with an open circle. 7 over 2 is the same thing as 3.5. 1, 2, 3, 4. 7 over 2 is right here. All right, if I multiply both sides by 2t minus 7, 5 greater than 2t minus 7. Add the 7. Divide by 2. 6 is greater than t. So 6 needs to be on my number line here. 3, 4, 5, 6. It's just greater than, and so I have an open circle. If 6 is greater than t, that's the same thing as saying t is less than 6, right? These are the same exact statement. 6 is greater than t is the same thing as t is less than 6. I can use this one and know that I need a graph to the left. And so I need a graph to the left, but I also need to avoid that red open circle. Here, I'll do it in blue. I need to shade this way, all the way out, avoiding that red open circle. And so my interval notation solution is everything from negative infinity up to 7/2, and then everything from 7/2 up to 6. Not including the 6 because this is strictly greater than. Here is strictly less than, right? And so no brackets at all on this problem. Here's another. Take a second, see if you could solve it. This is the last one. I'm going to unfreeze it in 5 seconds. X can't equal 6. And on the right side, I have what happens when you solve it. You multiply by x plus 6. 2 minus x equals 0. You can subtract the x, subtract the 2 or add the x. Add those items to your number line. 6 made the bottom 0, so it has to be an open circle. Since the sign in the problem was greater than or equal to, I put a closed circle on the 2. And since, let's see, how did I get this interval here? This should be greater than or equal to, shouldn't it? This should be greater than or equal to. This should be greater than or equal to. X should be less than or equal to 2. And what I did actually was I went through and just checked intervals. I just checked numbers in between to see what worked. Here's where I'm checking the -7. -7 did not work. Here's where I'm checking 0. 0 did work. And here's where I'm checking 3. 3 did not work. And so our interval notation is everything from -6 to 2, including the 2. All right, that's the end of a unit. You should feel good that you made it this far. You've made it officially through 3 units of 4 in college algebra, and you're almost to the end. Keep on trucking.